Yeah, okay, I will try to do it. So thank you, Etienne, for the introduction. And I will just start with the first slide, which is a very, very general slide, just to remember all of you that as long as we deal with self-assembly, we have a model molecule which are surfactants. And if you take such a molecule, such a surfactant, just by playing with the chemical nature of the polar head and with the chemical nature of the hydrophobic tail, you can achieve different type of self-assemblies, micelles, worm-like micelles, vesicles, some membranes, or some inverted micelles. And it is well known in the literature that all these things can be rationalized in terms of packing parameter, which depend on the volume of the surfactant and on the area that is needed for the polar head to sit at the interface. So we can have different kind of self-assembly by playing with the chemical nature of the surfactant. But the thing which is also nice is that depending on the self-assembly, you can achieve different kind of properties at the macroscopic point of view. For instance, we all know when we want to wash our hands, not our hands, our hair, with a shampoo, that it's better to have worm-like micelles inside your shampoo in order to have shampoo that will display some nice rheological property when you will want to make it flow in your hand when you want to wash your hair. And if you have some membrane phase, we also have nice macroscopic properties from the rheological point of view, because this is one way to achieve fluids that will display a yield stress. So this is what we know with surfactant. And now, if we want to mimic this property at the macromolecular scale, if you want to replace the surfactant by a polymer, so you just have to take this small molecule to make it much more bigger, and you have to replace the polar head by a hydrophilic block and the hydrophobic tail by a hydrophobic block. So each time you will see something in red, this block doesn't like water, and each time you will something in blue, this block likes water. So what is the main purpose in replacing surfactant by block copolymers? You can achieve exactly the same property, but with far less number of molecules, which is better from the cost point of view for a given application. It's also much better for the environment. You can have exactly the same properties as a surfactant, but at a length scale which is much more bigger. If you have a complex formulation of this block copolymer, maybe since you have blocks, macromolecular blocks instead of small molecules, there will be much more resilience when you will wish to formulate them for a given application. And we all know that if you take block copolymer instead of a surfactant to achieve the stability of latex particles, you increase the stability by several order of magnitudes. The main things that we want to know is that if we play with the chemical nature of this block copolymer, is it possible, as long as you put this block copolymer in water, to achieve exactly the same self-assembly that has been encountered with surfactant molecule? So if we go to the literature, a lot of work has been done by the group of Heidi Eisenberg in Canada regarding polystyrene block copolymers, and the hydrophilic block consists in polyacrylic acid. And if you look at this literature, you can see that if you take a diblock based on polystyrene and polyacrylic acid, it's possible to obtain spherical micelles, worm-like micelles, some also vesicles, and some membrane phase. So apparently, block copolymers display exactly the same polymorphism as surfactant. But the thing which is very strange is that if you look carefully at the chemical nature of the block copolymer, you can see that you can obtain worm-like micelles, spherical micelles, and membrane with the same block copolymer. It's not possible with a surfactant, because if you have a given surfactant, you have a given packing parameter, and it's not possible to have worm-like micelles and spherical micelles with exactly the same surfactant. So this is very, very strange because here, if you fix the chemistry, you can achieve different kinds of self-assemblies. You also can obtain self-assemblies that have never been reported for surfactants. For instance, you have this exotic structure, which is called large compound micelles. And you can see that these micelles are much more bigger in terms of size. Look at the scale bar, which is given there, than the regular spherical micelle that you can obtain with a block copolymer. So the thing which is very important to say is that here, with a single chemistry, you can achieve plenty of different kinds of self-assembly. And in order to achieve this different kind of self-assembly, you have to play with the procedure that you will use to disperse into water this block copolymer. So if I want to be more precise, here I use a block copolymer based on polystyrene and polyacrylic acid. I dissolve this block copolymer inside dioxane, and if I dissolve this inside dioxane, I have a solution of my block copolymer, and I will add drop by drop some water. So if I take this system in dioxane and I had some drops of water, you see that my polymer has the tendency to self-assemble within spherical micelles. Now, if I add more and more water, these spherical micelles have the tendency to turn into worm-like micelles. And if I add more and more water, I have the tendency to obtain some vesicle. So you can see that here I fix the chemistry of my block copolymer, and I only play with the process that I use to disperse this polymer inside the solvent in order to achieve this different type of morphology. The thing which is very nice is that I can turn my vesicle into spherical micelles if I add more and more dioxane to my solution. So here we have the tendency to say that I can display different kind of morphology with my block copolymer, exactly like what has been reported with molecular surfactant. But the main difference that you have between block copolymer and molecular surfactant is that each stage that you can see here are completely frozen. It means that you have no exchange between free molecule of block copolymer inside the dispersed solvent and the self-assembled polymer inside these different types of morphology. So each state is completely frozen or dead from the dynamic point of view. But you can see that even if you have dead situation, you can have reversibility from one structure to another just by playing with the amount of dioxane and of water that you use to obtain this self-assembly. Another way to achieve self-assembly of block copolymers is to use the so-called polymer-induced self-assembly principle. And here you can see that when you consider a polymer which is based on polystyrene as the hydrophobic block and a copolymer based on ethylene oxide metacrylate and some polymetacrylic acid, by increasing the polymerization degree of the polystyrene block, you can turn your spherical micelles into worm-like micelles and into vesicles. But here again, all these systems are completely frozen from the dynamic point of view. There is no exchange between free polymer chain inside the solvent and the self-assembly. It's very, very important because here, these systems behave more like fibrils than the worm-like micelles that I've shown you with molecular surfactants. So what is the consequence of that? If you take amphiphilic block polymer and you put it in water, you have the possibility to have self-assemblies of various shapes by playing with the dispersion path that you follow to achieve the dispersion of this polymer in water. But if you have polystyrene block and if you heat your polymer above the glass transition temperature of polystyrene, these self-assemblies will turn into spherical micelles. And it's not possible to go back to the self-assembly that you have formed in the pristine state of your polymer. You have no possibility to go back to this self-assembly. What you can do also is to play with the ionization degree of acrylic acid. And here, the thing which is very important is that here it's not acrylic acid, it's metacrylic acid. Here it's acrylic acid. But in all these situations, acrylic acid is under a neutral form. If you try to ionize acrylic acid, you will turn all your self-assembly into spherical micelles. And it's not possible to go back to the situation that you have here, to the pristine state of the polymer. Which means that the big problem of block copolymers, self-assembly, is that they are frozen. And once you play with them in terms of temperature of ionization, they are not reversible. So it's very, very funny because if you look at the literature on block copolymer, you have a lot of paper. But if you look now at the real application of block copolymer from the industrial point of view, in solution, you don't have such a lot of application. Why? Most of the time, when you deal with a block copolymer, the self-assembly is frozen. So here, I've drawn a micelles of a block copolymer, okay? And if I want this system to be dynamic, I must have the possibility for one polymer chain to go out this micelles, which require for the hydrophobic block to have a kind of mobility in order to move inside the micelles. And it also requires some energy for these diblock chains to escape from the micelles and to go to water. Okay? So the mobility is related to the glass transition temperature of the hydrophobic block. If you use polystyrene, we all know that the glass transition temperature is pretty high. That is why most of the times when you have a diblock copolymer based on polystyrene, you form frozen aggregates. But if you now replace these polystyrene blocks by a block of poly N-butyl acrylate with a glass transition temperature which is far below room temperature, the funny thing is that you have a micelles with a liquid core, but here again, you form frozen aggregates. Why is so? It's because if you want to remove these polymer chains from the micelles, you must spend a kind of energy, and this energy has been computed by theoreticians, and they have shown that this energy was related to the polymerization degree of the hydrophobic block to the power 2/3, and was also related to the surface tension of this hydrophobic block with respect to water. So if the polymerization degree is high, or if the surface tension of the hydrophobic block is high, the energy that you have to give to your block copolymer to escape from one micelles is pretty high, and there is no way to achieve it at a given temperature. So how can we decrease the surface energy? We can add a co-solvent. This is how you obtain most of the time self-assembly of block copolymers by using the nano-precipitation process. You can add surfactant that will decrease the surface tension of the hydrophobic block. But the big problem of this both solution is that as long as you remove the surfactant or you remove the co-solvent, you have no more a system which is at equilibrium. Another way is to decrease the surface tension of the block, the hydrophobic block, with respect to water. So if you look at the value for polystyrene, this value is pretty high because it's equal to 32 millinewton per meter. If you look at poly N-butyl acrylate, you can see that this value is also pretty high. This is why even if the glass transition temperature of this block is far below room temperature, you form frozen aggregate as long as you have poly N-butyl acrylate as the hydrophobic block. But if you now go to polymer with much less value of the surface tension, for instance, all that we know about derivative of ethyl acrylate, you can see that we have system with a very low surface tension that will show some equilibrium property and self-assembly driven no more by the preparation path that you follow to make them, but much more by thermodynamics. And we all know the family of pluronics, which are maybe the only block copolymer that are used by a lot of people in different application fields. This system, they display from the point of view of their hydrophobic block a very, very low value of their surface tension. That is why most of the time pluronics display equilibrium property based on thermodynamics and not on kinetics. What I will show you today is that another way of decreasing the surface tension of the hydrophobic block with respect to water is to try to use hydrophobic block that have been tempered, and I will explain you what means tempered. So actually, what I will do is that I will compare pure diblock copolymer based on poly N-butyl acrylate as the hydrophobic block and polyacrylic acid as the hydrophilic block with block copolymers where I've added on purpose an amount of acrylic acid within the hydrophobic block. Okay? And I will show you that this system, when they are pure, they display frozen property. But when you are able to incorporate within the hydrophobic block some tiny amounts of hydrophilic subunits, they will display living property. I will try to explain you how we can synthesize them, and I will try to show you how we can ensure that this system display properties at thermodynamic equilibrium. I will show you how it's possible to tune these properties. And most above all, I will show you that this procedure, this idea is rather universal and is not related to a single chemistry. So here, this is the really tough part of my talk because I'm not a chemist at all, a polymer chemist, and I will try to discuss some chemical slides. So I hope that you will not ask me too much detailed question about this because it will be quite difficult for me to address your question. So in order to obtain our block polymer with hydrophobic block tempered by hydrophilic subunits, we have decided to make them with RTRP, which is controlled radical polymerization. First, we will achieve a copolymer of N-butyl acrylate and tertiobutyl acrylate. So we make this first block in order to obtain a block where we will have a statistical distribution of both comonomers within the block. You can see that by plotting the kinetics of reaction, we have for each monomer and for the sum of them something that display the property that you expect for a controlled radical polymerization. You can see that the dispersity of the polymer is pretty low, and you can see also that we really have a living nature for this polymerization, which means that we have almost no termination or transfer reaction during the polymerization. The thing which is very, very important to see from this plot is that the copolymer is purely statistical, which is very important. Once we have this first block, we will extend it with a pure poly tertiobutyl acrylate block. And you can see from the GPC curve that we have here that we have an increase in the molecular weight of the polymer and almost no more residual first block, and that we keep the dispersity of the system pretty small. And then here we have nothing that is hydrophilic. So what we will do is that we will achieve a selective acidolysis of the tertiobutyl acrylate unit in order to transform them into acrylic acid. In order to do this, we use acetic acid. And you can see from NMR that it's possible to transform only tertiobutyl acrylate into acrylic acid. You can see this from NMR spectrum, which are given there. So this is the polymer that we have. We have a diblock with a hydrophobic block within inside this hydrophobic block, we have some amounts of acrylic acid, and we are a pure hydrophilic block, which is based on polyacrylic acid. Most of the results that I will show you are obtained with block copolymer, where we have roughly 50 mol% of acrylic acid and of N-butyl acrylate within the hydrophobic block. So now I will try to show you and to convince you that it's possible to make the difference between a frozen system and a living system from a different technical point of view. And the first technique that we will use to ensure that the system is kinetically or thermodynamically driven is small angle neutron scattering. So I will first look at data obtained on a diblock copolymer where the hydrophobic block is purely based on N-butyl acrylate. And here, this is the scattering profile, scattering intensity as the function of the scattering wave vector that I obtained for a pure diblock copolymer at different ionization degree for the acrylic acid. And this system is dead, as you can see from the nice photo of this singer that maybe the older of us recognize, maybe not the younger of us. So we typically measure this kind of scattering profile. I'm not sure that everybody is fully confident with scattering techniques. That's why I've prepared 1 or 2 slides regarding this technique. So scattering, in brief, it's a very, very natural phenomenon, and it's due to the interaction of light with matter. Scattering is responsible for the blue color of sky during the day, or for the red color of sky at sunset. It's also responsible, and a lot of us in France have faced this situation this morning. We call this the Stendhal effect, which is due to scattering of light by the mist. I mean the droplet of water that stand in the atmosphere, and it's also responsible for the green color that you can observe when you are at the pole of the Earth in September or at spring. So, in order to understand scattering, what I've drawn is here it's a kind of object. It's an aggregate based on small beads here. And I want to measure from the scattering point of view this object. The 2 information that I want to derive for this object is its molecular weight, its size. To do this, I will measure the scattering intensity of this object in solution as the function of the scattering wave vector. And this scattering wave vector is actually the small red circle that I've drawn here. The size of this circle is the inverse of the scattering wave vector. The scattering wave vector is given by this equation, and you can see that it depends on the wavelength of the light that I use to send on my sample, and it also depends on the scattering angle at which I achieve my measurements. So in order to understand this value of the scattering wave vector, you just have to figure out that when you want to take a selfie of yourself, if you are too close, you will only make a picture of this part of you. If you are very far, you will have your whole head inside the selfie. So a scattering experiment is exactly the same. If I want to picture the whole aggregate, I have to increase the size of this red circle, which means that I have to decrease the value of Q. How can I decrease the value of Q? I can decrease the angle of observation, and I can increase the value of the wavelength, which means that you can, if you decrease the value of Q, have a photo of your aggregates, of the overall aggregate. You can measure its size and you can measure its molecular weight, which is very easy if you increase the wavelength. I mean, if you achieve light scattering experiment. And now, if you want to look to part of your aggregate, if you want to take a selfie very close to your face, you have to decrease the value of Q, and in this case, you have more information about the molecular inside of the object that you are looking at. And to do this, you have to do some X-ray or neutron scattering, or you have to increase the angle of observation at which you make your measurements. So what you measure is the scattering intensity as a function of Q. If you go to low value of Q, you measure something which is related to the molecular weight of your system. If you go to high value of Q, you start to go inside your system. And when you go from a plateau value of the scattering intensity and you see a sharp decrease of the scattering intensity, this sharp decrease occurs at a value which is indicative of the inverse of the size of the particles that you are looking at, which means that if you have bigger particles, you have an increase of the intensity at low Q, and you have a shift of your curve towards lower value of Q because the size is bigger. I hope it's clear for everybody. So if I go back to this result, what you can see here is that whatever the ionization degree of acrylic acid, all the curve decrease in terms of intensity exactly at the same value of Q, which means that the size of the particles have not changed at all, whatever the ionization degree. You can see also that if you look now at very low value of Q, where you measure the molecular weight of your system, you have a sharp difference, a small difference between all the system, but this difference is very, very small, which means that here, whatever the ionization degree, the micelles have always the same size and almost always the same molecular weight, which is typical of a system which is frozen. Okay? Now, if I look at a living system, exactly the same, but I incorporate within the hydrophobic block some acrylic acid subunits, you can see that if I play with the ionization degree from blue to black, I have a sharp decrease of the scattering intensity at low Q, which means that I have a decrease in the molecular weight of the system. And I also have a shift of my curve towards higher value of Q, which means that I have a decrease in the size of the system. So here, if I play with the ionization degree of acrylic acid, my cells at low ionization degree turns into smaller and smaller micelles as long as I increase the ionization degree of my system. And the nice thing is that if now I go from a high ionization degree up to a low ionization degree, you can see that all the curves superimpose, which means that my system is fully reversible in terms of ionization degree and the influence of this ionization degree on the size and the molecular weight of the particles. Here, there is something which is very important, is that when I mean ionization degree, what is this ionization degree? Because I have acrylic acid inside the hydrophobic block, and I have acrylic acid inside the hydrophilic block. So when I talk about ionization degree, it's an average ionization degree. Okay? But if you can ionize it without any difficulties. Okay? So when I discuss ionization degree, I will always focus on the average ionization degree, the core of the micelles being more difficult to ionize than the corona of the micelles. So if I look the aggregation number as a function of the ionization degree for a frozen system, you can see that the aggregation number, which is the number of polymer chain inside the micelle, is constant whatever the ionization degree for a frozen system. But you can see that for a living system, the ionization degree decreases almost by 2 orders of magnitude as long as you ionize your system. And you can see that it's perfectly reversible. So we could conclude that this system is completely living. But there is a big problem, because I told you in the introduction that if you play with the amount of water of dioxane, you have reversibility from a spherical micelle to vesicular self-assembly, but each state was completely frozen. Here, it's exactly the same. A very, very important message is that reversibility does not mean thermodynamic equilibrium. So this result is not a proof that the system is dynamic. The only way to measure dynamic is to measure a relaxation time. If you look at the literature, you can measure this relaxation time by doing stop flow measurements with scattering techniques. We have decided to measure this relaxation time with another technique. And this technique is rheology. But in order to measure this relaxation time, you have to focus on tri-block copolymer rather than on diblocks. Because if you take a tri-block copolymer at thermodynamic equilibrium, if you put this in water, this tri-block will have the tendency to form flower-like aggregates. And upon increasing concentration, these flower-like aggregates will have the tendency to form a network by sharing a polymer chain between them. And if this network is living, you can have exchange of polymer between all the flowers. And this exchange, you can measure it with rheology. How can you achieve that? You just have to measure the elastic in red and the viscous in blue modulus of this network. And if you have a relaxation time, I mean, if you have at low frequency something that behaves like a liquid, and at high frequency something that behaves like an elastic fluid, the crossover point will give you the relaxation time of your system. And this relaxation time is related to the lifetime of one hydrophobic block inside the network. For a frozen system, you can see that if you measure G prime in a field symbol as a function of the frequency, you have a plateau, which means that you have no relaxation time, which means that you have no exchange dynamic. But with our system, where we have on purpose added some hydrophilic subunits inside the hydrophobic block, we measure a relaxation time, and this relaxation time is related to the lifetime of a hydrophobic block within the network. The nice thing is that these relaxation times depend on the ionization degree of acrylic acid inside the polymer. And here you can see that if I increase the ionization degree, I have the tendency to have a shift of the crossover frequency towards higher value, which means that I have a decrease of the relaxation time. But the nice thing is that if I take all this curve obtained at different ionization degree, and if I try to build a master curve with them by shifting the curve with respect to a reference curve, all the curves superimpose, which means that whatever the ionization degree, the relaxation process always occurs in the same manner, which is the extraction of one hydrophobic block from the core of the flower-like micelles. And a very, very important result is that by playing with the ionization degree of the acrylic acid, you can have systems that flow like water or systems that behave like very, very strong gels. And you can play with this relaxation time by 11 order of magnitude. The very, very important thing is that from the point of view of pH, you have this shift or this transition from a solid hydrogel towards a liquid into a very, very small and tiny window of pH. But here, if I go to very low ionization degree, which means to pH roughly equal to 4.5, I have one exchange of one block every 3 years. Which means that if you want to measure this, you have to put your sample on the rheometer and to wait 3 years just to have one exchange, which is obviously impossible to achieve, except if you have a dedicated rheometer to achieve this. So how is it possible to measure this relaxation time, which means that your system is almost frozen, with the lab scale? It's very easy. Here you have a living system. Here you have a dead system. For human being, between the birth and the death, there is a phenomenon which is very important, which is called aging. It's exactly the same for our hydrogels. When you have this hydrogel and you put this hydrogel to a given ionization degree of acrylic acid, you can see that in time, this hydrogel displays some aging. It means that before dying, the hydrogels get older, older, and older. And if I plot the relaxation time as the function of the lifetime of my hydrogels, all the gels start to be very young at the beginning, and they have the tendency to age with time. But at the end, they reach, I'm sorry, my pointer is quite lazy. At the end, they reach a state which does not depend anymore on the age of the system. So it's very important because now if I look from the application point of view, I have the possibility to use this system to control the rheology of complex fluid. If you go to an industrial company and you say, I'm able to design an hydrogel that will display a frozen nature, they will tell you, okay, nice, but if I have to wait a lot of time before having this system at equilibrium, it's not possible. So what you can do is to start with a system which is at thermodynamic equilibrium when it's not aged at all. You can try to reach this aging and this death much more faster just by playing with temperature. So what you can say is that the problem is that this window where you have a transition between a gel and a liquid is very, very tiny, and you should be able to play with it, because if you want gels to be obtained at much lower pH or much higher pH, you have to be able to control this pH window where the transition occurs. And one way to achieve this is to play with the amount of acrylic acid that you add to your hydrophobic block. So if you have tiny amount of acrylic acid, or if you have big amount of acrylic acid, you can see that if I plot the relaxation time that I measure with rheology as a function of the ionization degree, you always have the same tendency, but the transition between a strong gel and a liquid occur at different value of pH, which is very, very important. So it means that I can design a system that will be a gel at 4, or that could be a liquid at a pH equal to 4, just by playing with the composition of the polymer. The nice thing is that this is what we measure from the experimental point of view, but can we predict this behavior? And yes, we can predict it, because I can try to build a curve just by looking at the ionization degree, not of all the acrylic acid, but only acrylic acid which are inside the hydrophobic block. And you can see that if I plot the relaxation time as a function of the ionization degree of this block, all the curve almost superimpose, maybe not when you have too high amount of acrylic acid inside the hydrophobic block, but it means that all the behavior is related to the ionization of this temper block within the polymer. So you may say that, yeah, it's nice, thank you, but it only works for acrylic acid. Actually, if you look at literature, people have been able to design exactly the same system with acrylic acid, but with another hydrophobic block, styrene in statistical block copolymers or in gradient block copolymer. This is the work of Denis Bendejac in United States, or the group of Laurent Billon in Pau. It's possible also to use other pH sensitive units instead of acrylic acid, such as dimethyl aminoethyl methacrylate. This is work that has been obtained in Le Mans by Fabien Duterte, or in the group of Rachel O'Reilly in UK by, I don't remember his name, but his family name is right. And it's also possible to use other hydrophilic units which are no more sensitive to pH, but maybe to temperature. And this is work that we have done with Kostas Titsinianis in Greece. The main point here is that the distribution of the hydrophilic unit within the temper hydrophobic block must be very, very well controlled, because we have shown with the group of Bernadette Charleux quite a long time ago, that if instead of having a statistical distribution of each unit within the hydrophobic block, you have a gradient distribution of both units within the hydrophobic block, this system was completely frozen. So now what is nice to do is to play with life and death of this system. And what I will show you is why is it nice to have system where you can control the thermodynamic equilibrium. The first thing that I will show you, the first result that I will show you is a result where I have a frozen hydrogel and I will dilute this frozen hydrogel to a pH where the system is living. So this is how the molecular weight of the system vary with time. When you look at your system during 1 month, you start at a pH of 4.2. After 1 month, keeping the pH constant, the molecular weight has decreased by a ratio 1.5. Okay? But now, so when you go from frozen to frozen, there is a slight decrease of the molecular weight of the system upon time. But now, if you do exactly the same, you start with a frozen system and you dilute the system to a pH where the system is living. You can see that within 1 month, you start at the same point, but after 1 month, the molecular weight of the system has decreased by 3 orders of magnitude. So you have been able to transform your frozen system by dilution into a living one. The nice thing is that if you take all this curve, you are able to build a master curve, which means that the degradation process of your hydrogel is exactly the same and does not depend on the target pH that you reach, but the speed of degradation is related to the difference of the initial pH and the final pH of your system. And the nice thing is that if you look at this degradation kinetics, which is displayed by the circles on this curve, where we show the relaxation time measure initially divided by the relaxation time measure at pH 4.8. So this is the data which are here. When you increase the pH, you have a sharp decrease of the degradation time. And if you compare this with the relaxation time that we measure with virology, it's exactly the same behavior, which means that the degradation of your system is related to the exchange of the hydrophobic block within the hydrogel. Why is it very important? I will show you with this movie. I hope that it will work. So here you have bits of hydrogels. It's a confocal measurement, and it's at a pH where the system is frozen. I will dilute this hydrogel towards the pH where the system becomes living, and you will see the consequence on the structure of the hydrogels. Okay, I hope you will see it. It doesn't work. Nice. Okay, so I'm sorry. So what you should have seen is that you have a swelling of the hydrogels, and then the hydrogels disrupt into small bits, small pieces, which is very, very nice if you want, for instance, to use these hydrogels as the cargo of the molecule, because you will have the tendency for this molecule to be vectorized. Second nice thing about thermodynamics. You can blend two systems which are at thermodynamic equilibrium very easily. So this is an example of what we have done. So if you take a pure block copolymer, you self-assemble it, you measure the scattering intensity as a function of Q, and you have the data which are shown in white. And now you mix two block copolymers which have been tempered, but the mixture has exactly the same composition as this neat block copolymer. And what you can see is that if you mix these two block copolymers, they display exactly the same structure as one block copolymer. Why is so? It's because you have thermodynamic equilibrium. So here you can save a lot of time, because if you have two block copolymers with different composition, just by mixing them, you can achieve all the composition in between. You can then target one property, and you can optimize then the structure of the polymer just by mixing two of them. Another way of saying this is that if you mix a micelles of one block copolymer with a micelles of another block copolymer, you are able to make mixed micelles between both. But it doesn't work every time. For instance, this is the aggregation number of micelles of block copolymer, where the hydrophobic block has been tempered with acrylic acid, as a function of the composition. So here you have a system, this polymer, at this ionization degree, forms no micelles at all. The same polymer with less acrylic acid inside the hydrophobic block has a tendency to form micelles with an aggregation number almost equal to 10. And then you mix this one and this one. And what you can see, I'm sorry, somebody is trying to reach my apartment. So what you can see is that if you mix this one and this one, you have no mixed micelles between these, both polymer. Why? It's because this one doesn't want to aggregate with this one because it's very happy by itself. Okay? But now, if you mixed both polymer, but the first one now is aggregated because you have decreased the ionization degree of this polymer, you can see that it's possible here to obtain mixed micelles between the polymer DH40 and the polymer DH60. And how can you see that you have mixed micelles? Is that if you just have an average between this micelle and this micelles, you should have an aggregation number that vary along this solid line, and actually the mixture does not behave as an average between this and this. So you have mixed micelles. So it's very nice because if you try to achieve exactly the same thing with frozen system, it's impossible. Now, if you mix tri-block copolymer, it's very nice because you can achieve a given relaxation time, no more by playing with the ionization degree of your block copolymer, but just by playing with the composition of your mixture. If you take, for instance, two polymers, one with a very, very high relaxation time here, and one with a very low relaxation time here, and if you mix them together, you can have an average relaxation time, which means that your gel consists in both, in a mixture of both these block copolymer inside water. And it's even possible if you have a dead hydrogel to have a relaxation time. So the dead hydrogel is here. You have no relaxation that you can measure from the point of your rheology. And if you mix these dead hydrogels with a living hydrogel, you can measure relaxation time, which means that you are able to transform something dead into something which is living. So, as a conclusion, a very important message. Reversibility does not mean equilibrium. One way to achieve self-assembly of block copolymer at thermodynamic equilibrium is to temper the hydrophobic block, decrease their surface tension, by adding some small hydrophilic unit inside them. The nice thing is that in this case, you can predict all their properties in terms of aggregation number, relaxation time, by looking at this tempered block. It's then possible to achieve much more easier, in a much more easier way their blending. You can also control the degradation of the hydrogel that you can form with them, but you have to follow some rules because sometimes when you mix blue and yellow, instead of having green, you can have these things where you have no mixing, which is possible. What we are doing currently with the group of Maud Save and Elise Degnaud in Pau is to try to use the same strategy, I mean tempering the hydrophobic block, but in this case to obtain anisotropic nanostructure and no more spherical micelles. So this were scientific conclusion. Non-scientific conclusion, which is very good for somebody like me who turns older and older. It means that aging can be good. Blending can also be good. So it's always nice to mix different kind of people together to have at the end something that look fancy. And it also means that resurrection is possible, at least for hydrogels. And I just remind you that we have somehow some hydrogels because our body contains from 60 up to 65% of water. So it means that maybe very rapidly resurrection will be possible for us also. Just as a conclusion, I'd like to quote this sentence that has been written by Louise Bonaparte, a sister of Napoleon, and who said, "Working is easy, pleasure is more difficult to achieve." And it's possible to achieve pleasure when you work if you have the possibility to work with nice people. So in my case, it was possible with Olivier Colombani and Taco Nicolai, who work in my lab. It was also possible with students, Élise Lejeune, now in Pau, Céline Charbonneau in Le Mans, and Lionel Daubert, who works in Saint-Étienne. Arti Shedge and Myriam Marie de Souza Lima, who comes from India and from Brazil. It was also possible to achieve a lot of pleasure by working with Bernadette Charleux, Virginie Poncinet in Bordeaux, and Jacques Chestin in Saclay. This work has opened the possibility to make some collaboration with the group of Rachel O'Reilly in UK, with Daniel Wright and Joseph Patterson, and also with the group of Kostas Titinianis in Greece. I also want to thank Etienne, who has organized this stay-at-home polymer webinar. And regarding all this stuff, resurrection, life and death, if you have the possibility to come to Le Mans in a more or less near future, I advise you to visit the cathedral, because inside the cathedral, you have the oldest stained glass window that stands since the 11th century inside the cathedral, and that represents the resurrection of Christ. Here you have Mary, and you can see here maybe the feet of Christ who has decided to go to heaven. Just a last conclusion, I work a lot on amphiphilic block copolymers. I've done recent work with the group of Simon Harrison and the group of Mathias Desterac in Toulouse regarding multi-block amphiphilic polymers. But I also work a lot on liquid-liquid phase separation in order to obtain water in water emulsion and capsules based on protein. And I also work a lot on the degradation mechanism of plastics in water, which is very important in terms of the formation of macroplastic and nanoplastics. Thank you for your attention, and thank you, Etienne, for organizing all this. And if you have any questions, do not hesitate to ask them now or later.
Yeah, I can see you. Good afternoon, everyone. Yeah, it works. Okay, thank you, Christophe, for this very interesting talk. I think that many people around here are interested by the self-assembly of block copolymer, especially at SCPO, as you may know. So I will share this question session. So actually, there are two written questions from YouTube. So perhaps you can also read them from your computer.
I don't know.
Okay. Okay, so I will read them. So the first question for you: can you blend polymer that is not tempered with tempered polymer in the same way as polymer with different amounts of acrylic acid?
Okay. So I told you that you have to obey some rules in terms of blending. We have tried to blend frozen self-assembly with non-frozen one, and it was not possible to obtain hybrid self-assemblies. The only way to achieve this is at one stage, which is exactly what people do when they do a nanoprecipitation, to have a state during the processing and during the dispersion of your polymer where the system is at thermodynamic equilibrium. So the only way to achieve this in our case was to process the polymer at very, very high temperature in order to decrease in big extent the surface tension of the block, the hydrophobic block.
So there are some conditions.
Yeah.
Okay, it seems clear for me. So I guess for everyone. Another question about so what could we expect from a hydrophobic grafted hydrophilic polymer chain in terms of self-assembly?
So it's a very good question. I had 2 slides about this, but I removed them. You have exactly the same thing. I mean, if you take this tempered block and you graft it onto a polyacrylic acid chain, all the things that I've told you, the pH dependence of the relaxation time that you measure from the point of view of rheology, the fact that the behavior of the system is controlled by the ionization of this tempered block, all the things that I've told you are true, also holds. And we have published this in macromolecule papers 3 years ago. So if somebody is interested by this, I can give the reference without problem. 10 minutes before starting the presentation, I've removed these 2 slides in order to keep the presentation within the slot that was allowed.
So if the behavior is similar, did you still observe some differences in terms of value of relaxation time, for instance, compared to block copolymers?
Alors, the thing is that you measure exactly the same thing in terms of pH dependence of the relaxation time, but the absolute value is completely different because when you have a block copolymer, it's very easy to understand that if you apply a stress to your hydrogels, you just have one block to get out in order to relax this strain. But now, if you have a comb, you must have more than one block to extract from the core of the hydrophobic reticulation nodes of your system to relax the strain. So the relaxation time with grafted systems are bigger than the relaxation time that you measure for pure tri-block copolymer.
Yeah.
But the pH dependence is exactly the same shape.
Yeah, it makes sense. You are a very good teacher. So next question from YouTube also. Merci Christophe. It was a nice talk. The question, how did you manage to dye only your hydrogel for confocal analysis?
Okay. Here we just use rhodamine, and rhodamine is soluble inside the hydrophobic patch of your polymer. So actually, I'm only able to dye physically, it's not covalently bound to my polymer, but it's a physical labeling. And you can see that we see red things, so it just means that we have the hydrophobes inside.
Okay, so there is no covalent bonding.
No, it's only physical.
Okay. Yes, with a covalent one, you may modify the.
You have to do some chemistry. We all know that even if you keep the amount of dye low, you can play with the hydrophobic nature of this dye, and you can have some difference. The thing is that we have achieved rheology with physically labeled polymer in order to see if it was important on the relaxation time. And since we keep this labeling amount pretty low, we measure exactly the same thing with or without rhodamine.
Okay. Looks clear also for me. A question from Khalid. Thank you, Christophe, for this very interesting talk. So, very difficult question, I suppose. What is the consequence of using a living system on the stability of emulsion?
It's a very good point. The nice thing about a living system is that since it is a system that behaves like a molecular surfactant, from the point of view of stability, you may have an exchange of your polymer with the interface towards the solvent. But do not forget that since it's a macromolecular surfactant, you also have the possibility to have a protection of your droplets or of your latex by both electrostatic and steric repulsion. The thing that we have done a long time ago is that by playing with the dynamic, so if you take a system which is completely frozen, and you take this as the emulsifier, you can control the number of latex particles that you are able to transform, because each frozen micelle will turn into a particle. Now, if you have a system which is dynamic, you no more have this control, and you have something that really behaves like an emulsion polymerization, which means that you need several micelles to obtain one latex particle. So the point of view of using a dynamic or a frozen system is very good if you want to control exactly the number of particles you want to obtain at the end in your latex. And the second good things of having a frozen system, so I don't address the question of Khalid. I don't explaining what is the advantage of using a dynamic system. I explaining what is the advantage of using a frozen system. Is that if you have a frozen system and you mix it with a dynamic system, you can in this case prepare latex particles with two size distributions, small particles and big particles. And it's very good because you can achieve very high solid content, but you still have latex that are able to flow.
Okay, thank you, Christophe. Next question is from Etienne Gros. Did the hydrogel's resurrection trick works with water containing lots of ion, like in a living dead body?
So the thing which is very strange is that, yeah, we have done a lot of measurements with ionic strands and all this. You have the tendency to, all the measurements that I've shown you here, that I've not shown you because the movie didn't work at all, were achieved in a phosphate buffer where we control exactly the ionic strength of the system. So it was with quite a big amount of salt, I mean with a ionic strength which was quite high and which could mimic what you obtain in the body. So I don't think that you have such a big influence of the ionic strength on the result that I've shown you, but the relaxation times can be slightly affected by the ionic strength, which is result that we have published also quite a few years ago.
Okay, so ions are not an issue.
No, as long, because remember we have acrylic acid, so as long as the amount of divalent cation is low, it works perfectly. But if you have too much calcium, for instance, you will have the tendency to have some precipitation due to the complexation by acrylic acid.
Yeah, yeah, yeah. Another question from Victor. So he thanks you again. If I understand well, can we consider that polymer gelators and gelators in general are in fact super molecular surfactant or molecular surfactant with a high packing parameter value?
It's a very good point. So when Victor is dealing with gelator, I think he's talking about organogel or something like this.
We may assume, yeah. Yeah.
Yes. So the problem of organogel is that most of the time these systems are also completely frozen. So here, the organogelator, most of the time, they have the tendency to form fibrils, and these fibrils will entrap the solvent and will turn the solvent into a gel. The only system which are at equilibrium are the systems that have been designed by the group of Laurent Bouteiller in France, and Meyer also have done some work about this, where so the famous EHUT molecule, where the system is at equilibrium, and in this case, it really behaves like worm-like micelles of surfactant, but more in organic solvent. So the same problem of frozen or not frozen system is encountered with organogelator. Now, I'm not sure that as long as you are dealing with frozen system, you can discuss the property of your system in terms of super packing parameter. Because as long as the system is no more driven by thermodynamic, but much more by kinetic, as I shown, not me, but from the literature, with a single packing parameter, which is ruled out by the chemistry of the system, you can obtain spherical micelles or worm-like micelles on these icons.
Okay. Okay, thank you, Christophe. There is no other question from people here or in YouTube. I have one or two, if you don't mind. Actually, if you have also tackled this issue of equilibrium in the dilute state. I mean, you know that many people are using amphiphilic block copolymer for drug delivery applications. So usually it's done in quite diluted conditions, but still the issue of equilibrium remains the same. So have you also studied this equilibrium aspect in the dilute condition?
So all the light scattering results that have been obtained in order to derive the aggregation number, they have been obtained in the diluted state in order to ensure that we measure a true molecular weight and not an apparent molecular weight. So all the results that I've shown on aggregation number as a function of the composition of the mixture and all this, they have been obtained in the diluted state. Only rheology has been achieved at pretty high polymer concentration, and not that high because the percolation concentration of the system can be of the order of 10 grams per liter. So it's not that concentrated. But the thing which is very important is that one way, for instance, to ensure that the system is at equilibrium or not is to prepare a solution at high concentration, a solution at low concentration, and to dilute the solution at high concentration to the same concentration as the one that has been prepared at low concentration. And if you don't have the same results in terms of aggregation number, size, structure, it's a way, it's a hint that your system is not at equilibrium.
Okay.
But it takes quite a lot of time to do this systematically.
Yeah, you need to dilute every system.
And again, for a lot of this biological application, people use pluronic, not only because they are biocompatible and but also because this system, since the surface tension of the hydrophobic block is not that high with respect to water, these systems are truly at thermodynamic equilibrium.
And on my second question, perhaps, is on a kind of absolute scale of equilibrium states. How would you compare your temperate system, for instance, with surfactants?
Okay. So the thing which is very funny is that when you discuss with people who have done a lot of work on worm like myself, based on surfactant, not on polymer, they always tell you that if you look at the relaxation time that you measure with rheology, you have something which is of the order of, let's say, 10 milliseconds or something like this. So you expect the system to be at equilibrium very easily. But actually, if you take a surfactant that will have the tendency to self-assemble within worm like myself, in order to reach an equilibrium state, you need to wait something like sometimes 2 or 3 weeks. So the funny thing is that each step is very rapid. The exchange of one molecular surfactant from the worm like myself towards the water is very, very fast. But now, if you want to measure the relaxation time of the overall self-assembly, it can take a lot of time to reach a thermodynamic equilibrium. In our case, we have seen that sometimes you need to wait 1 or 2 days before having a system at equilibrium, even if the relaxation time of the exchange is very fast.
Okay, so there is a kind of local and global relaxation time.
Exactly. You have something which is very local due to single molecule, and you need to expect sometimes some cooperative motion between all of them to have something which is really at equilibrium state.
Yeah, to get the wall structure. Yeah,
exactly.
This is really interesting. Okay, so I do not see any other questions. So I thank you again, Christophe, for this very interesting talk. I think that many people were interested. And I'll just remind that everybody can replay your presentation on YouTube and put likes if they like. Thank you, Etienne.
Thank you.
So we can close the session, Etienne? I like. Okay.
Okay, thank you.
Thank you very much.
Yeah. Yes. I don't know which Christophe or who Christophe you are talking about because
both we enjoy.
Have a nice weekend. Bye bye.
Thank you. Bye bye. Bye bye. See you at 4.